Spectroscopy. Spectroscopy is the general field of study that measures and interprets the electromagnetic spectra that result from the interaction between electromagnetic radiation and matter as a function of the wavelength or frequency of the radiation. Its wavelength or frequency measured by spectrographic equipment and other techniques in order to maintain information concerning the structure and properties of matter. Special measurement devices are referred to as spectrometers, spectrophotometers, spectrographs, and spectral analyzers. Most, most spectroscopic analysis in the laboratory starts with the sample to be analyzed. Then a light source is chosen from any desired range of the light spectrum. Then the light goes through the sample to a dispersion array or a diffraction grading instrument and is captured by a photodiode. And for astronomical purposes, the telescope must be equipped with a light dispersion device. Spectroscopy as a science began with Isaac Newton splitting light with a prism and was called optics. James Clerk Maxwell came to include the entire electromagnetic spectrum. Spectroscopy involves the splitting of light by a prism, diffraction grading, or similar instrument to give off a particular discrete line pattern called a spectrum, unique to each different type of element. It's a fundamental exploratory tool in the field of astronomy, chemistry, material science, and physics, allowing the composition, physical structure, and electronic structure of matter to be investigated at the atomic, molecular, and macro scale and over astronomical distances. Important applications include biomedical spectroscopy in the areas of tissue analysis and medical imaging. Spectroscopy is used in physical and analytical chemistry because atoms and molecules have unique spectra. As a result, the spectra can be used to detect, identify, and quantify information about the atoms and molecules. Spectroscopy is a measurement of absorption and emission of light and other radiation by materials. Electrons in atoms and molecules have quantized energy levels, and electromagnetic radiation can only be received and emitted at specific wavelengths. As a result, spectra are dotted with lines of absorption or emission rather than just uniform. Principles behind spectroscopy. Spectroscopy is based on the principle of Beer-Lambert's law. According to this law, when a beam of monochromatic light is passed through a sample solution, the intensity of absorption is directly proportional to the path length of the light and the molar concentration of the solution, and this is given by the equation and where terms are explained: absorbance, molar absorption coefficient, molar concentration, and optical path length. So what is the principle behind spectroscopy? Beer-Lambert's law. Major types of spectroscopy: visible or ultraviolet spectroscopy. UV or visible spectroscopy is the most common and widely used spectroscopic method. This is an absorption or emission spectroscopy. Visible spectroscopy is based on the fact that atoms are capable of either emitting or absorbing visible light. In UV visible spectroscopy, light is passed through a sample at a specific wavelength in the UV or visible spectrum. Visible spectroscopy is based on the fact that atoms are capable of either emitting or absorbing visible light. In UV or visible spectroscopy, light is passed through a sample at a specified wavelength in the UV or visible spectrum. UV spectroscopy is used to estimate the concentration of protein and DNA in a sample. This is done by comparing the intensity of light passing through a sample to the intensity of light passing through a blank or reference sample. Here is a picture. First, a mirror is there, D2 lamp and tungsten lamp, filter. Through this filter, a monochromator is there, and after that, beam splitter, mirror, reference is there, sample is there, and data processing, photodiode, and data is readout. So this is the structure of UV spectroscopy. Mirror, D2 lamp, tungsten lamp, filter, monochromator, beam splitter, mirror, reference and sample along with data processing, photodiode. We need major parts like filter is a must and monochromator, mirror is a must, tungsten lamp will be there and mirror is a must have and beam splitter is a necessity. Reference along with sample will be providing and data processing and photodiode is a very important part. Then that data is readout. Atomic emission spectroscopy. AES or atomic emission spectroscopy measures the emission of radiation from atoms in excited states. This method utilizes the atoms excited from a heat of a flame for light emission, which helps in the analysis. Atomic absorption spectroscopy. Atomic absorption spectroscopy or AAS quantifies the absorption of electromagnetic radiation by well prepared neutral atoms. Unlike AE spectroscopy, a flame of lower temperature is used so as not to excite the sample atoms in this method. This method is predominantly involved in the quantification of metallic substances. This is because it has greater sensitivity and accuracy when compared to other methods. Infrared spectroscopy. It is a powerful tool used for a variety of samples. IR spectroscopy depends on the change in dipole moment. IR spectroscopy is absorption spectroscopy that measures absolute frequencies at which a sample absorbs radiation. And what is a major point related to it? Depends on the change in dipole moment. Infrared spectroscopy is dependent on the change in dipole moment. It is used in both qualitative and quantitative analysis. Absorption of infrared radiation causes changes in molecular vibrations within molecules, and infrared spectroscopy is based on measurements of how bonds vibrate. In molecules, atom size, bond length, and bond strength vary, hence, the frequency at which a specific bond absorbs infrared radiation varies throughout a range of bonds and modes of vibration. IR source is there, reference and monochromatic system will be there, sample, splitter, detector, and readout. IR source, monochromatic system, reference, sample, splitter, detector, readout. Raman spectroscopy. Raman spectroscopy depends on the change in polarizability of a molecule. Currently, there are 6 major types of Raman spectroscopy in use. Although the advantage of this method is that it requires little or no sample preparation. Raman spectroscopy is inexpensive and rapid when compared to IR spectroscopy. Raman spectroscopy is a non-destructive chemical analysis technique that yields detailed information about chemical structure, phase, and polymorphs, crystallinity, and molecular interactions. It is based on light's interaction with chemical bonds within a substance. Raman spectroscopy is used in solid-state physics to characterize materials, monitor temperature, and determine the crystallographic orientation of a sample. A solid material like a single molecule can be distinguished. Laser is applied. Raman scattering is happening. Alpha scatter, alpha laser, Stokes Raman scattering, and Rayleigh scattering is also happening. Nuclear magnetic resonance spectroscopy. Nuclear magnetic resonance spectroscopy or NMR is an analytical chemistry technique that functions based on electromagnetic fields. This spectroscopy is used in quality control and research to determine the content and purity of a sample as well as its molecular structure. NMR spectroscopy enables quantitative analysis of mixtures obtaining. NMR spectroscopy enables quantitative analysis of mixtures containing known compounds. Quantitative analysis of mixtures containing known compounds. Nuclear magnetic resonance spectroscopy or magnetic resonance spectroscopy is a spectroscopic technique used to examine local magnetic fields around atomic nuclei. The NMR principle normally involves 3 successive steps in a constant magnetic field: the alignment, polarization of a magnetic nuclear spins, and the disturbance in this nuclear spin alignment by a weak oscillating magnetic field, commonly referred to as a radio frequency pulse. The detection and analysis of electromagnetic waves generated by the sample's nuclei as a result of this disruption. Magnet is there, sample tube will be inserted into that, magnet controller, detector, RF transmitter, absorption, magnetic field, and printer. FTIR spectroscopy. Frontier transmission Fourier transform infrared spectroscopy is a technique for obtaining an infrared spectrum of a solid, liquid, or gas absorption or emission at the same time. An FTIR spectrometer collects high resolution spectral data over a wide spectral range. Compounds such as compounded plastics, mixes, filters, paints, rubber coatings, resins, and adhesives are swiftly and clearly identified using FTIR spectroscopy. It can be used throughout the product lifetime, including design, manufacturing, and failure analysis. Its resource: interferometer, sample detector, interferogram, FFT computer, and spectrum. X-ray spectroscopy. X-ray spectroscopy. X-ray spectroscopy is a technique for detecting and measuring photons or light particles with wavelengths in X-ray region of the electromagnetic spectrum. It is used to assist scientists in understanding an object's chemical and elemental properties. Sample is there, electron beam is hidden to that, X-ray signals are there, detector, amplifier, computer, display, data output device. First we will be hearing the electron beam into the sample. Later, X-ray signals are produced: detector, amplifier, computer, display, and data output device. Spectroscopy uses and applications. In proteomics, this technique helps in the characterization of proteins. In the pharmaceutical industry, spectroscopy helps in the analysis of bioactive compounds and metabolites. In the agricultural industry, spectroscopy is used as a nitrogen sensor and helps to estimate the concentration of nitrogen in rice. It helps to detect contaminants and adulterants in the food industry. Spectroscopy also enables water quality testing. It helps to determine cell growth and viability of bacterial samples. Proteomics, pharmaceutical industry, agricultural industry, contaminants, food industry. Spectroscopy is also used in water quality testing, cell growth and viability of bacterial samples. Spectroscopy is used to determine the structure and functional groups in organic compounds. It helps to determine the presence of biomolecules. It is used to indicate the presence of toxins and pollutants in the environment. It is also involved in the astronomical studies. Spectroscopy enables the detection of catalysts in a chemical reaction. It can also be used as a detector system for other analytical procedures like HPLC. Spectroscopy facilitates forensic studies as well. And ultraviolet visible spectroscopy. UV spectroscopy. Visible spectroscopy refers to absorption spectroscopy or reflective spectroscopy in part of ultraviolet and the full adjacent visible regions of the electromagnetic spectrum. The only requirement is that the sample absorb in the UV vis region be a chromophore. The only requirement is that the sample absorbed in the UV region will be a chromophore. Absorption spectroscopy is complementary to fluorescence spectroscopy. Parameters of interest beside the wavelength of measurement are absorbance, transmittance, or reflectance, and its charge with time. Most molecules and ions absorb energy in the ultraviolet or visible range. They are chromophores. The absorbed photon excites an electron in a chromophore to higher energy molecular orbitals, giving rise to an excited state. For organic chromophores, 4 possible types of transitions are assumed: pi, pi star, n, n star, pi star, sigma, sigma star, and n, sigma star. Beer-Lambert law. When A is a measured absorbance, formal dimensions but generally reported in absorbance units. I/O is the intensity of the incident light at a given wavelength. I is the transmitted intensity, L is the path length, and molar absorptivity and extinction coefficient. Beard's law. According to Beard's law, when a beam of monochromatic radiation passes through an absorbing medium, the intensity radiation decreases exponentially with an increase in the concentration of the absorbing medium. In other words, absorbance is directly proportional to the concentration of the absorbing medium. Absorbance is directly proportional to concentration of the absorbing substance. Lambert's law. According to Lambert's law, the rate of decrease in the intensity of radiation with the thickness of medium is directly proportional to the Intensity of light. Rate of decrease in the intensity of radiation is directly proportional to the intensity of incident light and the thickness of a medium. Instrumentation. Source of light. Tungsten lamp. It can offer sufficient intensity. Carbon arc lamp. It can provide high intensity light. Filters and monochromators. This can convert the polychromatic light into monochromatic light. Filters. There are two types: absorption filters, interference filters. Next, monochromators like prism type and grading type. So prism type is there. Two types of prism types: dispersive type of prisms, litro type of prisms. Grating systems: diffracting type grating, transmission grating. Sample cells, there are also called cuvettes. Then sample volume, shape of the cell, cylindrical or rectangular cells. Material, for visible region, color corrected fused glass. For UV region, cells which are made up of quartz. Detectors, the UV visible spectrometer types, this are called to be photometric detectors. Photovoltaic cell or barrier layer cell, photoemulsive cells or phototubes. Then photomultipliers will be there. Photovoltaic cell or barrier layer cell, photoemulsive cells or phototubes, photomultiplier tubes. Then monochromatous, prism type, grating type, and detectors. UV visible spectrometers, this can be called as photometric detectors. Photovoltaic cell or barrier layer cell, photoemulsive cells or phototubes, photomultiplier tubes, whatever it may be. Then structure, that tungsten lamp is there, monochromated, reference and sample, detector, data output. First, tungsten lamp and my monochromator, reference, sample, detector, data output. This is a picture representing that. So D2 lamp and tungsten lamp, mirror, filter, monochromator, mirror, beam splitter, sample and reference, data processing, photo, diode will be there, and data readout. This is the apparatus. The region covered falls between 180 nanometer and 800 nanometer through though some instrument manufacturers provide absorption range extending up to 1010 nm. Absorption in UV visible region arises due to transitions between electronic energy levels of absorbing molecules. A typical spectrum comprises of a plot of absorption versus wavelength. Solids are seldom studied directly due to random refraction and reflection losses on the surface. Such solids can be dissolved in suitable solvents, transparent in the absorption region of interest. The solutions can be studied in transparent cells or cuvettes made of quartz or glass. Gases can also be studied in such cells provided with gas-tight stoppers. Applications: the absorption of a reactant or product at constant wavelength provides a means of monitoring the progress of a chemical reaction. The absorption of a reactant or a product at constant wavelength provides a means of monitoring the progress of a chemical reaction. Clinical studies using indirect measurement of reactions characterized by enzymes can also be carried out. DNA or deoxyribonucleic acids are involved in protein synthesis in living cells and preserves genetic information. Changes in pH or heating can lead to denaturation with the resultant increase in the absorption by 260 nm. Monitoring absorption at this wavelength is useful for denaturation monitoring. DNA or deoxyribonucleic acids are involved in protein synthesis in living cells and preserve genetic information. We all know that. Changes in pH or heating can lead to denaturation with the resultant increase in absorption at 260 nanometer. Monitoring absorption at this wavelength is useful for denaturation monitoring. Appearance of additional peaks due to presence of impurities can help establish purity or of standard materials. Absence or presence of functional groups results in absence or presence of their characteristics absorption bands. Identification and quantitative determination of polynuclear aromatic compounds. Non-absorbing molecules can be estimated by combining with the derivative forming molecules that produce new species or new species with absorption characteristics in the UV or visible region. Quantitative estimation of ionic solutions of transition metals or complex forming ligands. Versatility of UV visible spectroscopy has been adapted to detection in UV HPLC technique. It is more particular detection mode in HPLC for organic molecules. The simplicity, accuracy, and cost effectiveness contribute to its popularity in areas such as pharmaceuticals, life science, foods, environmental studies, forensics, and mineralogy. Solvent effect in water and in ethanol, wavelength, absorbance, etc. Now let's learn some other topics in the next video. Thank you.